Alright, so now that we got all of our previous discussion out of the way, we can return to looking at root systems. Today our first topic is the isomorphism theorem of root systems, I guess, and it's just called the isomorphism theorem here. So, our setup here, we're going to let L be a semi-simple Lie algebra over a algebraically closed field f of characteristic 0. We're going to let H be a maximal toral subalgebra of H, and phi in H star be the roots of L relative to H. We saw before that the rational span of our roots in the dual space of H is of dimension L over the rationals, where L is the F dimension of H star. Extending the base field from rationals to reals, we get an L-dimensional real vector space E spanned by phi. Also, the symmetric bilinear form dual to the killing form is carried along to E, which makes it a Euclidean space. Then by an old theorem, phi is in fact a root system in the axiomatic term in our Euclidean space E. We aim to show that the root system determines the semi-simple Lie algebra up to isomorphism. So if two semi-simple Lie algebras have the same root system, they have to be isomorphic. first off, a reduction to the simple case. Starts with the proposition. Let L be not a semi-simple, but a simple Lie algebra. Then our root system is irreducible. Proof. Suppose, by contradiction, that phi decomposes as phi1 union with phi2, where of course phi1 and phi2 are orthogonal to each other under our form. If alpha is in phi1 and beta is in phi2, then the form of alpha plus beta on alpha is non-zero. And likewise the form on alpha and plus beta on beta is non-zero. So alpha plus beta cannot be a root. And so the eigenspaces of alpha and beta have bracket 0. Thus the subalgebra K and L generated by all L alpha for alpha in phi1 exclusively is centralized by all L beta for, of course, beta in phi2. With K a proper subalgebra, as the center of L is just 0. However, we also see that K is normalized by all L alpha for alpha in phi1. Hence, it is by all L alpha for alpha just being any root from anywhere. Hence, it extends to all of L. Thus, K is a non-trivial, proper, ideal of L, but we know that L is simple, and so this is a contradiction. We're going to let L be a semi-simple Lie algebra. L can be written uniquely as a direct sum L1 plus through to Li of simple ideals. If H is a maximal toral subalgebra of L, Then it has a corresponding decomposition. Okay, these are indexed up to t, not I, where these HIs are just generated by being the intersection of the associated Li in H. Each HI is a total subalgebra in Li and is in fact maximal as a total subalgebra. As any total subalgebra, Li larger than Hi would be total in L, centralize all H sub j distinct, and generate with them a larger toral subalgebra that is larger than our H. Let phi denote the root system of each of our elements in the direct sum, Li and the direct sum of L, relative to the part of our maximal toral subalgebra in that sum in the real vector space EI. If alpha is in H at phi of I, we can view alpha as a linear function on H with alpha of Hj being 0 when j is outside of our I. Then alpha is a root of L relative to H with L alpha being inside of Li. Conversely, F alpha is in phi, then the bracket of Hi with L alpha is non-zero for some I, or else H would centralize L alpha, and then L alpha would be L inside of Li. So the restriction of our alpha to Hi is a root of Li relative to our Hi. Thus, this is just decomposing our root system. We decomposed into the union of phi ends and the generated Euclidean space as the direct sum of E1 through ET. Why did I use n as my final subscript? Thus we get a corollary, which is going to go on a new page. Let L be a semi-simple Lie algebra with maximal toral subalgebra H and root system phi. And decomposition L as L1 plus through LT, decomposing it into simple ideals. Then each HI as the intersection of our maximal torsal algebra with each LI is a maximal toral subalgebra of our Li with corresponding root system phi as a subsystem of phi such that phi is the union of phi1 through phi t. This is decomposes our root system into irreducible components, of course. And from this we see that all we need to do now, we can characterize all semi-simple Lie algebras by the root systems just from characterizing the simple ones by the root systems. Now with all the setup out of the way, let's look at the isomorphism theorem. So, proposition. Let L be a semi-simple Lie algebra with H being a maximal torsal algebra and phi being a root system of L relative to H as before. Let delta be a base of our root system. Then L is generated by the root spaces L alpha and L negative alpha for alpha in delta. And so, trivially from that, by arbitrary non-zero x alpha in L alpha, y alpha in L negative alpha for alpha across delta. The proof. let beta be an arbitrary positive root relative to delta, of course. We have seen that beta can be written as the sum of alpha I, we'll say from 1 to s, where each alpha I is a root, is a base root, positive, simple, whatever the word for that is, and each partial sum from a1 through some ai is a root. This J just be less confusing, and we also know the bracket of two root spaces is the root space of the sum of the roots when all three of these are roots. By induction on S, we can see that L beta lies in the subalgebra of L generated by all of our L alpha for alpha in alpha. Similarly, if beta is negative, it lies, then LB lies in the subalgebra of L generated by all L beta, of all L negative alpha for alpha in delta. I don't know why I said beta. Since L is H plus the sum of these root spaces, the disjoint union, and H is the sum of the brackets of L alpha and L negative alpha, we are done. Now, if X alpha is an element of L alpha and Y alpha is an element of L negative alpha, both non-zero, with H of alpha being defined, if you recall, as the bracket of X alpha and Y alpha, we can call a set of X alpha and Y alpha with or without RH, since we can derive it from the other two. A standard set of generators for L. What are they doing? Recall that H alpha is the unique element of the bracket of L alpha and L negative alpha, in which alpha takes the value 2. Sorry, give me 1 second. Things are happening here. Alright, so if L with H and L prime with H prime are pairs of a simple algebra and a maximal toral subalgebra, we want to show that an isomorphism of the corresponding root systems phi and onto phi prime will induce an isomorphism of L onto L prime, sending H onto H prime. We know that an isomorphism from one root system to another induced by an isomorphism of the ambient Euclidean spaces not necessarily an isometry, not necessarily an isometry, but can be assumed to be one by scaling the inner products, as that won't affect the root system at all. We also want to notice that the isomorphism from phi to phi prime extends uniquely to an isomorphism phi of H star to H prime star. Since phi spans H, which itself induces an isomorphism from our H to H prime by the killing form identification of H and H prime with H star and H prime star. And that is if alpha to alpha prime denotes our map of the root, our isomorphism of root systems, then pi of the corresponding t alpha is equal to t prime of alpha prime. And since this map comes from an isometry by force, we have that pi of h alpha is equal to h prime of alpha prime, as h alpha is, recall, just 2t alpha over the form of alpha with itself. Since h and h prime are abelian Lie algebras, you can regard pi as an isomorphism. Of Lie algebras. We now need to extend pi to an isomorphism of L into L prime. Which we will obviously, which must send a root system to its a root space to its corresponding root space. Now, it says the question arises: to what extent can we hope to specify in advance the element of L prime alpha prime to which a given x alpha of L of a root space should be sent? Now, alright, where does our extended pi, which I'm going to write as pi, send x alpha in L alpha to inside of L prime alpha prime? Note that for x alpha, x beta, and x alpha plus beta, with the bracket of x alpha, forgot the x, bracket of x alpha on x beta being x alpha plus beta, forcing that the bracket of x of their prime, everything's prime, is going to line up. So this gives us some structure to work with. Lots of primes just everywhere. So we should focus on simple roots where we have independent choices for all this. And we have one theorem, which I think we're going to spend basically the rest of the video going over. And it says something. Let L and L prime be simple Lie algebras over F with maximal Toral subalgebras H and H prime with root systems phi and phi prime. Suppose an isomorphism of phi onto phi prime as alpha of alpha prime, inducing our pi, sending h to h prime. Fix a base delta in our phi so that delta prime being our alpha prime under this original isomorphism for alpha in our base being a base of phi prime. And for alpha and delta, alpha prime and delta prime, we want to choose arbitrary x alpha and L alpha, x prime alpha and L prime alpha prime, i.e. an arbitrary algebra isomorphism p prime from pi alpha sending L alpha to L prime alpha prime. And then there exists a unique isomorphism. We can just overload our pi here. Isomorphism extending pi of h to h prime and extending all pi alphas for alpha being a root. Now pi is unique, obviously, as x alpha determines y alpha in L in the root space is a negative root such that the bracket of x alpha and y alpha is h alpha, which generates L. Existence is pretty straightforward, it seems, too. So if L and L prime are going to be the same, then the direct sum, which is a semi-simple algebra with unique simple ideals of L and L prime, should include a subalgebra D resembling our diagonal subalgebra, which is isomorphic so our proper diagonal subalgebra is a subalgebra of L plus L. It's isomorphic to L under projection in either direction. So, and we see that x alpha determines a unique y alpha and L negative alpha for which the root, the bracket of x alpha and y alpha is h alpha, then we get the same structure in L prime. So we let D be generated by x bar alpha being x alpha, comma x prime alpha prime, with corresponding y bar alpha in y as y alpha with y prime. How did I butcher an equal sign that bad? Y bar alpha being equal to y alpha with y prime alpha prime, and h alpha bar being the collection of h alpha, h prime alpha prime. So why is D proper as a subalgebra? Because you might have, like, it says conceivably you could have like both an x alpha with x alpha prime and also x alpha with 2x alpha prime, which would generate all of L prime, which is then all of L, which is then everything. So we know that phi and phi prime are irreducible since we're in a simple context. Let beta and beta prime be the unique maximal roots of phi and phi prime relative to delta and delta prime, which correspond under our natural map phi to phi prime. So we're going to choose arbitrary non-zero x in L in the root space of beta, x prime in the root space of beta prime. We set x bar to be the pair x, x prime inside of L plus L prime. And let M be the subspace of this L plus L prime spanned by all of the adjoints of y bar alpha 1 composed through to adjoint of y bar alpha m on x bar, where a alpha is some element of the root system. We allow repetitions, and these obviously belong to the root system of beta minus the sum of the alphas plus the corresponding on L prime. With M, the intersection of M with L beta plus L prime beta prime being one-dimensional. So our diagonal is a proper subspace. Now, we want to show that D stabilizes M which we're going to do by the generators of D. So we see that the adjoint y bar alpha stabilizes M, and by induction from the bracket of H with Y alpha is a multiple of alpha. So the adjoint of our H also stabilizes M. Now for simple roots alpha, the adjoint of X alpha commutes with all adjoints of Y for gamma unless gamma equals alpha. Applying the adjoints of our X bar alpha to the above, and by that I mean this whole M is a subspace by all M as a subspace spanned by these collections of adjoints on X. If we apply these to that, we can just move it past each adjoint of Y bar gamma except for our adjoint of Y bar alpha, not gamma bar alpha, although my writing's probably not too easy to differentiate between the two. Giving an extra summand. Which has already been taken care of. Since the adjoint of X bar alpha of X bar is 0 whenever alpha is in our root, since we have alpha plus beta is not a root by maximality, the adjoint of X bar alpha stabilizes our M. Thus D is a proper subalgebra. Or else M would be a proper non-zero ideal of L plus L prime, and thus would be equal to L or L prime. Now we claim the projections. They don't label them, so I'm just going to use a one-off term here. Projections, call them C alpha from D onto C1 of D onto L, and C2 of D onto L prime are isomorphisms. So essentially we can have an isomorphism between the two by going backwards, by taking whatever we're in up to D and then down to the other side. I'll show their isomorphisms. These are homomorphisms, trivially. and onto by the definition of our diagonal, or it's more of a pseudo-diagonal. Suppose the intersection of D and L is non-zero, where L is the noting L is the kernel of C2. Then D contains some non-zero pair W with 0. So D contains all adjoints of adjoint Z alpha 1 composed through to alpha adjoint of Z alpha S on W with 0 for each alpha I being a element of the base or negative, and Z alpha being X alpha or Y alpha. These elements then form an ideal of L, and so RL. So D includes L. By symmetry, D includes L prime, so all of L plus L prime, which we already know is not the case, so the intersection with the kernel has to be 0, so it is an isomorphism. Now, note that observe that the isomorphism of L onto L prime as I guess what it would be phi2 of C2 C1 inverse sends X alpha to X prime alpha prime and sends H alpha to H prime alpha prime. So coincides with pi on H. And we're finally done. This extends to this we know extends to semi-simple algebras trivially. Now we can also write down an explicit presentation of L of our L with generators X alpha, Y alpha, H alpha, for alpha a root in a base, with relations only depending such that the constants involved only depend on our root system. And then any other similar L prime with isomorphic root system is isomorphic. we'll prove this later on. It's a bit more difficult, but we get sort of an existence theorem for semi-simple algebras. Not sure quite what that means yet, but we're getting there. Yeah, thanks for watching, I guess. I gotta close this video.